Welcome to Quantum Maniac. We're going to start a series of videos away from the mathematical part, in which we will be explaining some concepts about quantum computing. But to understand how a quantum computer works, first we need to understand how a classical computer does. Do you really know how they work? Have you ever wondered about it? If you really want to understand how a computer works, follow me on the next 20 minutes, as we are going to try and explain it in the most simple possible way. Before understanding what a quantum computer is and how quantum computing works, we must understand about classical computing. We have all heard the fact that our current computers work with bits. And when we ask, what are actually bits? The answer normally is that they are ones and zeros. What does it actually mean that a computer works with ones and zeros? The main thing is to understand that a bit is a concept. Bit is the acronym for binary digit. And being binary means it can represent two different things. You probably know we can use different systems to count. In the binary system, there are only two options, 0 and 1. In the decimal system, which we are more accustomed to use, we use 10. Regardless of the system we use, when we reach the last number, we simply add a new position and start counting again. That is, if we're using decimal, whenever we reach 9, we increase the position to its left by 1 and start over again. But I don't think I have to teach you how to count, right? And that way we can continue to infinity. With the binary system we do exactly the same. We start with 0 and the next number would be a 1. We have no more options, so now we move one position and start over again. 1 0, then 1 1. The next one, 1 0 0, 1 0 1, 1 1 0, 1 1 1. And like before, we can continue to infinity. This means that any decimal number has its equivalent in the binary system. They are simply different ways of representing the exact same thing. For example, the number 348 in decimal is the number 1010111100 in binary. We can use any base, like hexadecimal that uses 16 different elements. But we will talk about that in a different video. In general, we use the decimal base in our everyday life. See if you can imagine why. But how do we differentiate between two different bases? Like, how do I know that this binary number refers to the number 348 in decimal? And it's not 101,011,100. If there is any chance of error, the base is normally specified as a subscript at the end of the number, like this. And why might we be interested in using the binary system? Wait, we'll get there. We've said that a bit is a concept, and that it represents a binary element that therefore has two different states. Imagine a coin, it can be heads or tails. Well, then a coin can be considered a bit. Or imagine a lamp, it can be turned on or turned off. A lamp is also a bit. Any item that clearly represents two and only two different states is a bit. Think about it. There are many things that can be used as a bit. An open or closed door, a lit or extinguished candle, a full or empty glass of water. But here it is very important to understand that there are only two different options in binary. If the glass has little or a lot of water, it doesn't matter. One state is if it has water, and the other state is if it doesn't. The door can be completely open or slightly open. It doesn't matter. We're only considering two states, open or closed. This will be very important to understand what comes next, so please don't forget it. Okay, we now understand the concept of a bit. This means that we understand that we can use any bit to represent anything that is binary. Let's take the example of the lamp that can be on or off. Now, we only need to define what each state represents. We can say, for example, that if the lamp is on, it means true, and if the lamp is off, it means false. That way, someone could ask us questions and we could answer only by turning on or off the lamp, given that the questions can be answered with true or false. Or we can decide each state to represent something different. For example, we could agree that if it's on, it means yes, and if it's off, it means no. Or that if it's on, it's day, and if it's off, it's night. Or that if it's on, it means 1, and if it's off, it means 0. Do you get where we're heading? So when someone tells us that a computer works with ones and zeros, It looks like we're getting closer to understand that. But then, what is a bit in a classical computer? What does that binary concept represent? So think for a moment, what is a computer made of? Of electronic circuits, right? What can we use in a place where electricity passes through as a bit? Well, similar to the example of the lamp, we can say that if electricity flows through the circuit, that can be one of the states and represent a 1. And if there is no electricity current, then it represents the other state and become a 0. This way, we have just built an electronic binary system. As the passage of electricity or not through a circuit is very well explained with our lamp example, let's stick with it for a moment. Then what do we do now with this idea? Okay, we know that if we have a lamp, we can represent 2 states, if it's on or off, and we just need to determine what each state represents. For example, let's use a 1 and a 0. But then, what if we put 2 lamps together? Now we can actually represent 4 different states, 0, 0, 0, 1, 1, 0, and 1, 1. We can continue increasing the number of lamps, and that way we will increase the number of states that we can represent. The formula is very simple. With x bits, we can represent 2 to the x possible states. This leads us to another important concept. Bits are the smallest unit of information. Imagine for a moment that I want to remember the number 181. It is very important for me not to forget that number. Okay, an option is to write it down, but let's try a different method to remember it. In binary, this number is represented with 10110 and at home I have a series of spare lamps. So I put of them one after the other and I decide to plug the first one but not the second one. I plug the third and fourth one. I don't plug the fifth one but I do plug the sixth one. I leave alone the seventh one and I do plug the eighth one. Now, at any moment, I just need to come home, turn on the power, and look at the lamps. Those will represent a binary number, and that way I will know the number I wanted to remember. This way, we have just built a memory. It is a very, very small and impractical memory, but it's capable of storing certain information. Now, let's imagine that we are significantly increasing the number of lamps. That means we're increasing the capacity of our memory. The number that we will be able to store will increase as we add more lamps. Even we can devise a way to group the lamps together so they represent different things, or that each number represents something different. For example, I can decide that the number 1 represents an A, the number 2 represents a B, and so forth. With enough lamps or bits, we can get to store the Quixote or even the National Library. But we will talk about this in a different occasion and delve into the fact that with just a simple bit, grouping them together in a very smart way and with the only representation of ones and zeros, we can store incredible amounts of information. But let's get back to what concerns us in this video, which is basically trying to understand how a computer works. We have already seen that bits in a computer correspond to the flow or not of electricity in their circuits. If electricity passes, we have a 1, and if it doesn't, it's a 0. As in the previous example of the door or the glass of water, the amount of electricity that goes through the circuit doesn't matter. Whether it is much or little, we just consider if electricity is flowing or not. And to achieve this, computer uses something that's called a transistor. We can also talk about them in a different video, as understanding what they are and how they work will help us understand even more about computers. But for now, let's think of them as the shut-off valve of a pipe. It allows or does not allow the current to flow. Well, but everything we have seen so far doesn't really explain the most important ability of computers, which is precisely computation. Computers are especially useful not because they store information, but because they can process it and because they can do calculations. Then how do they do this using our famous bits? Okay, so now we're going to delve into the world of logic. And we're going to enter this world through some very special doors. First of all, we're going to understand that a computer is an extremely complex device. But like most complex things, at its core it's just an intelligent combination and coordination of much more simpler concepts. For a computer to do what it does, it needs to process information, which ultimately boils down to performing mathematical operations or moving information from one place to another. We already know that we can store information in bits, but now we're going to see how to perform a calculation using these same bits. They say that the transistor is one of the most important inventions in the history of mankind. Certainly, it has been the one that has allowed us to develop electronics as we know it today. The transistor, or transfer resistor, is a small electronic component consisting of 3 pins. It is mainly a switch between the collector and the emitter that is operated through a small current in the 3rd pin, the base. That is, if there is only electricity in the current or there is only electricity in the base, nothing happens. But if there is current in both, then the internal switch is activated and allows the current to flow through the emitter. By combining transistors, we can create what we call logic gates. Imagine that we have 3 lamps, and 2 of them are connected to the 3rd one, and this one will only light up depending on the states of the other 2 and how they are combined. An AND logic gate will light up if and only if the other 2 lamps are on. An OR logic gate, on the other hand, will light up if either of them or both are on. Logic gates can represent their states through what we call truth tables, like these ones. They represent the 2 input entries and the expected output, based on how they are combined. Okay, so how can we build logic gates in a computer? The answer is that we only need to combine transistors in a very clever way. Look at this example. In this scheme, our circuit has a current source, VCC, through which electricity circulates. And then we can make current pass through points A or B. With how they are connected and already knowing how a transistor works, you will see that the output corresponds to that of an AND gate. Let's see an example. This is the truth table of an AND gate. What this means is that when input A it's a 0 and input B it's a 0, the output should be a 0. We know how a transistor works, so electricity will flow through only if we have current through the VCC and through point A. In this case, if we have a 0, it means that no electricity is going through A. Therefore, here it will never continue. As the flow won't continue through the circuit, that means that B won't have electricity going through here either. Therefore, the output would be a 0. So when A is 0 and B is 0, the output is 0. Let's see what happens if we put current in 1 but not in B. We put electricity through the VCC, we put electricity through A, and these 2 will combine and go into B. But as we now know that B won't have electricity, then the current stops there, so out won't have any electricity left. Let's see what happens if we put electricity in A and B. So if electricity goes through here and then it goes through A, it will go by. Then it will enter B, and as we also have electricity in B, the flow will go through. And then we'll have electricity in out. With a 1 and a 1, the output will be a 1. Let's see an example with the OR gate. Again, here we have the truth table of the OR gate. And how it does, as you will see, we have 2 transistors and they are connected differently. They're quite independent. So the current can come to A, but it can also go through B at the same time. So what will happen if no current goes through A or B? Well, as we won't have any electricity going through here, we know that VCC current won't go through this transistor and it won't go through this one either. So the output is a 0. What happens if we put electricity in B but not in A? Well, In that case, we know that here it will stop, but the current will continue. And as we also have electricity coming from here, it will go to the output. With a A0 and a B1, we will have an output of 1. You can go through the other two examples to understand how this truth table works and how an OR gate works. There are different kind of logic gates, and we have seen the AND gate and the OR gate. We're not going to go in this video through all the different logic gates that we can create, but in order to understand what goes next, I would like to go through the XOR gate, which is also known as the exclusive OR gate. This is the truth table of an exclusive OR gate. As you can see, we also have 2 inputs and 1 output. The thing about this gate is that if A is 0 and B is 1, we will have a 1. If A is 1 and B is 0, we will have another 1. The state of both inputs needs to be different for us to have a 1. If they both share the same state, that means if they're both 0, or if they are both 1, then the output would be 0. We already know what a transistor is. We know how to combine transistors to create some of the possible logic gates. Now we're going to see how to combine logic gates to create a small circuit. And this circuit will allow us to add 2 bits. See, step by step and through very simple concepts, we are combining them to combine something that is a little bit more complex. Binary addition is basically the same as with decimal addition. So what do we do when we want to sum 8 and 5? Basically, we start at 8, we need to count 5. When we reach 0, we carry 1 and keep counting again from 0. This makes us reach the solution, 13. Although it seems more complicated if we try to explain it with words, basically it is counting and carrying 1 every time we finish a cycle. In binary, the only difference is that we reach 0 or we finish the cycle every 2 elements. So in order to add, we basically need to create a circuit that is capable of doing this. Take a careful look. In this case we have 2 inputs, A and B. But then we have 2 outputs. The first one, the sum, corresponds based on the inputs to an exclusive OR logic gate. And the second output, the carry, corresponds to an AND gate. It's basically as simple as that. With 2 current inputs and 2 logic gates connected to them, we just made a mini calculator. This circuit is known as a half adder and looks like this. Let's explain an example. So here we can see that we have created with our transistors 2 different logic gates. We have an exclusive OR and we have an AND gate. We only have 2 inputs, input A and input B, which will allow current to flow, depending on what we need to sum. So for example, let's imagine we want to sum 0 plus 0. Obviously, no electricity will go through here and no electricity will flow through here. Therefore, the result or the output in sum and carry will be 0 in both. So we know that the result of the sum of 0 plus 0 is 0 again. What happens if we want to sum 1 and 0? Okay, in this case, we're going to put electricity through A, so it's going to go into the exclusive OR gate. B has no electricity. Correct? So as we know with the exclusive OR gate, if we have flow in one of the inputs, then the result will be a 1. So the sum will end up with electricity flowing through. Therefore we have a 1 here. The current will also go into the AND gate, but in this case the AND gate, as you know, only works if the electricity goes through both inputs at the same time. So in this case, as we have electricity in A, but we don't have it in B, there won't be electricity to carry. So that's why we have a 0. For the next example, it's basically the same, but instead of in A, we have electricity in B. We will have a 1 in sum, but we will have 0 in carry. So 1 plus 0 or 0 plus 1 will give us 1 as a result. Now let's try to sum 1 plus 1, which will give us 1, 0. That's 2 in binary. Take into account that carry it's the number that we carry to the next position. So actually, if we put them together, this would be the number to the left and this one, the one to the right. Okay, so if we put electricity in A and we put electricity in B, that means here we have an exclusive OR that there won't be electricity here. When we go to the AND gate, we have electricity in both inputs. So we will have electricity in carry. That's why we have a 1. See, it wasn't so complicated, right? And we have basically built a very simple calculator. I think you're now getting to understand a little bit more how a computer works. Okay, I know this looks like a lot of fuss for summing 1 plus 1, but remember that complex things are always made of much simpler things intelligently combined. Before going to the next example, do you think you could come up with the circuit that we will need if we want to sum 3 bits? Now I'm going to show you the circuit, but if you want, pause the video a second and try to think, how would you do it? Trust me, it's a really interesting exercise, although it can be a little bit tricky. Okay, so this would be the circuit that we would need to build. And it's basically called a full adder. So in this case, we need 2 half adders combined with an OR gate. And that way we can sum 3 different bits together. If you don't believe me, just go through the truth table, follow what the current will do in each of the steps, and you will see that that's exactly what will happen. Let's go a step further now. We can easily add 3 bits in our head. But what if I ask you to build a circuit that is able to sum 2 different 8-bit numbers together? By the way, 8 bits is what we call 1 byte. Again, you just have to give it a little thought. But here you have the answer. Basically combining 7 full adder circuits and 1 half adder, we can create a circuit that allows us to sum 2 8-bit numbers. With this, you just built an 8-bit calculator. And all we have to do is let current pass or not through the different inputs in our circuit. And this, using the different half and full adders that we have, will retrieve an output or not, depending on how the electricity is flowing. Check that the count are connected to the next one. So we use the output of part of the circuit as the input of the next one. That way we can carry from one to the other on this binary system. Now just for a moment, take a good look to this circuit. Do they look alike? Are you starting to understand a little bit more how computers might work? Now, the only thing you need to do is to multiply this by a huge number. In this example, we have used a few transistors and we have achieved an 8-bit calculator. Nowadays, for example, look at this. This is Apple's A16 chip. You even might have one in your pocket right now. Do you know how many transistors it has? The number in the chip, the 16, should give you a clue. You only need to add a few zeros to that number. Because this chip, for example, has 16 billion transistors. Do you know how many calculations you can make with something like that? And the only thing you need to do is to make electricity go through the right places. And also remember that electricity can flow extremely fast. To help us understand the complexity, this is a simulation of electricity moving in a 6502 microprocessor, which was used in the Apple II or the Atari 400-800. We're talking about the 70s or 80s, and a whopping 4,528 transistors. This has been a short but intense video, in which we have learned what is a bit and how they can be used to build computers. If you want to learn more, in the next video, we'll see what a qubit is, its quantum counterpart, and the key to give those kind of computers such power. Don't miss it, because you're going to learn things that are going to freak you out. Now, if you have enjoyed this video, don't forget to subscribe so you don't miss the next one.